So we did a question about the filling of water bottles last time. And we decided not to reject our null hypothesis. We figured the variation in the amount of water being filled was within sufficiently small error range, was close enough that we didn't think there was anything wrong. On the other hand, with the mercury in our light bulbs from the example we did last Wednesday, what did we decide with that? We had a sample of light bulbs that we decided that the mercury level was an average of 3.59 milligrams instead of 3.5. And then we checked against the standard deviation that was known. Did we decide to keep or reject on that one? We rejected. So those were too much mercury for it to be random error. There's an important difference here. Giving something a rejection or an acceptance of the null hypothesis simply means that we do not find statistical evidence that says this is out of line. Problem number 25, page 333. The lifespan of xenon metal halide arc discharge bulbs for aircraft landing lights is normally distributed with a mean of 3,000 hours and a standard deviation of 500. If a new ballast system shows a mean life of 3,515 hours on a test of 10 new bulbs, would you conclude that the new lamp's mean life exceeds the current mean life at a alpha of 0.01? It also asks me for a p-value here. So now I can ask this question. I was told that the standard light bulbs have a mean of 3,000 hours and a known standard deviation of 500. That's a population, not from our sample. And then we take a sample of 10, and we see that they have an average of 3,515 hours because of this new ballast system. And we're asked, does the new system have an average that is exceeding the current average? Exceeding. What kind of test should I be using? Left to right. Because I want to know the unlikely thing is that the new mean will be bigger than, that's off to the right. So if I'm going to do a right tail, because of this word, then my null hypothesis is that the average is less than or equal to the benchmark. And my alternate hypothesis is that it is strictly bigger than. That's my right tail. And oh, right, they said that we wanted to use a significance 0.01. So I want to be 99% sure of my decision. Okay. I need two pieces of information. I need a test statistic, And then either I need a calculated z-value, a critical z-value, or I need a p-value based on that test statistic. Find me the test statistic first. Yes, the alpha is our, and do this again, I gotta go back and look, alpha versus beta. Alpha is our significance. That's how significant we find our finding. When we're done with this, we're like, oh, is this meaningful or not? So that's where we're defining our critical value. The test statistic is what we're going to check against that number. 3.257. Great. Now, there are two different ways to determine whether we accept or reject. I reject my null hypothesis if one of two things is true. The calculated statistic is larger than my critical value in absolute value. Or the p-value I get from here is smaller than my level of significance. What I am trying to say is that I think there needs to be a less than 1% chance that the average I got, 3,515, is happening randomly from bulbs whose real average is 3,000. There's only a 1% chance that that's not true. That's what the significance is here. Which one do you want to do? The p-value or the z-critical? Okay, z-critical comes off of my table. What do I need to find on my table to do z-critical? The right tail for 0.01. If the right tail is 0.01, that means that the rest of it is 99%, right? 98, 99%. There we go. 0.9901 is right about here. If I'm using my table, I can pull the number off of that. If you've written down the critical values from the table we came up with last week, what is it? Well, is that bigger than this? Which means reject. What does that mean in the setting of our problem? In terms of these new light bulbs, what can we conclude now? If I've rejected my null, this one's out, this one's in. The new light bulbs do have a higher mean lifetime than 3,000 hours. I don't know how much larger. I haven't done extensive enough testing, only tested 10 bulbs, to tell you what I think the new average should be, but it was not random chance that it happened to be so much bigger than 3,000 this time. How would I find a p-value? Say again? I can use either C1 or C2, but what am I going to look up? If I do that on table C2 shows me less than, right? And I'm looking at greater than. I want to look at that right tail. So this is 1 minus the chance that we are less than or equal to 3.257. Now, the downside is that my table only goes to 2 decimal places. So I have to use 3.26 on my table. And when I pull up 3.26 on my table, 3.2012345 I get 99944. And 1 minus that is 0.00056. Which is way smaller than the 0.01 that was alpha. So again, this confirms that I should reject my null hypothesis. We said we should reject when we're in this rejection region on the curve, right? And the rejection region starts at that critical value, 2.32. And the number we were at was 3.26, which is much further to the right. The other way to think of it is that the area inside the shaded region is 0.01. And then when I check for our shaded region, it's smaller than that. It's even further over. It's even smaller. There's even less of a chance that this happened randomly than I thought I would take as an acceptable risk. And thus, this result is statistically significant. Thus, our use of significance level. This result means something. It means the new bulbs last longer. How much longer? I don't know. But they definitely last longer based on this sample. Questions? If this number that we calculated, the p-value, was bigger than this, then I'd accept the null hypothesis. I would not have room to reject it. But that would have been the same thing as having a z calculated that was smaller than our z critical, right? It means that the area, we want to get this area. Now you're saying I got a bigger area. That means I have to be to the left, not further to the right. There is a problem with the sentence I just said in terms of this has statistical significance. When we say something is significant, we can mean it 2 different ways. I can talk about statistical significance. I did a calculation, this means something. And then we talk about practical significance. What if it turns out that the new average is not that much bigger than the old one? Would we spend all the money to switch to the new bulbs? No. But here, the new average appears to be substantially larger than the old one. So that's a measure of practical significance. our light bulb example. We rejected our null hypothesis. We said that that batch of light bulbs I tested had higher mercury than was acceptable by their claim. They claimed 3.5. We came up with 3.59. 0.09 milligrams of mercury. I have a challenge for you. With the piece of paper in front of you, I want you to tear off a corner of the piece of paper that you think weighs 0.09 milligrams. Do you think you can do that? I don't think I can get that small a piece of paper in my fingers. That's tiny amounts, right? Is it practically significant versus statistically significant? We said there was a statistically significant larger amount of mercury. Really? 0.09 milligrams. You're talking, wait, let me use the unit conversions. 90 micrograms. Right. I think there's more shampoo left over in your hair from your shower this morning. That's a tiny little amount. We filled the water bottles and we said, oh, the actual average was 10.016 ounces instead of 10 ounces. What's 0.016 ounces of water? Right? So there's statistical significance. There's practical significance. And the two don't mean the same thing. However, confusing the two deliberately is a statistician's best friend. I'm going to throw something I hope you all believe. Do you think smoking causes cancer? There was a lot of back and forth about that from the first Surgeon General's report up until just 10 years ago. The smoking lobby denied that there was any actual proof that smoking caused cancer. They're right, but there's a lot of statistical significance about the relationship. The first Surgeon General's report that showed a 20% increase in cancer diagnoses showed that the cancer rate went from 0.00001 to 0.000012. A 20% increase. Was it practically significant? Let me add another zero here. 1, 2, 3, 4, 5, 6. This is 10 out of a million people. This is 12 out of a million people. It's a 20% increase. And this was the smoking lobby's absolute comment. That's practically insignificant. Not that it's not statistically significant, but it's practically insignificant. They were lying their asses off trying to stay in business, but confusing and conflating those two ideas is something that happens a lot. Questions? I don't know what business you're going to be in. I don't know what analysis you're going to do, but at the end of it, you're going to get asked the question, should we do something about this? And that's where we cross the line from just chugging numbers to making a value decision. If I do this, it's going to cost me X, Y, Z, dollars, people, reputation, whatever. Is it worth it to do whatever this thing is? So our measurement of practical significance needs to come into play almost more than our statistical significance. That extra 9.09 milligrams of mercury may not be much per light bulb. But how many light bulbs does that factory make a month? Does it end up being kilograms of mercury? If so, we're going to have some really toxic fish eventually. In our discussion of these light bulbs, we knew the population of light bulbs had a standard deviation of 500 hours. Well, what if I don't know that? What if I don't know my population standard deviation or variance? What do? What I'm going to do is I'm going to do the same thing I did for confidence intervals. So now I get to go back and ask, what did we do for confidence intervals? Instead of z values, I used t values, and I used s instead of sigma. Now, the same thing that I needed in the intervals comes back again, and that's I need my degrees of freedom. And I have to remember that in this case, my degrees of freedom is one less than the number of things in my sample. It is still the same test, but instead of getting a z calculated value, I'm going to get a t calculated value. And my t calculated value is going to be computed exactly the same way. Average minus the benchmark over the standard deviation over the square root of my number of people. That's our standard error. Only instead of sigma, it's s. And I'll have to get a t critical. I'll get that from my table because I have all of those critical values based off of the degrees of freedom right here in Appendix D. Makes my life easier. The important thing is that I still need to make the same decision. Am I doing a left tail, a two tail, or a right tail based on the way the problem is written before I go and do any actual calculation? I need to write down my null hypothesis, my alternate hypothesis, so that I can set up the problem the way I want to understand it. Everything else works the same way. Problem number 37. The manufacturer of Glow-More flat white interior latex paint claims that one coat coverage of 400 square feet per gallon on interior walls. A painter keeps careful track of 6 gallons and finds coverages in square feet: 360, 410, 380, 360, 390, 400. At a significance of 0.10, does this evidence contradict the claim of the manufacturer? Let's do the same exact setup. They claim I should get 400 square feet per gallon can of paint. Then we did 6 of them, and we got 360, 410, 380, 360, 390, and 400. Does this contradict or support the claim of the manufacturer? What's the claim of the manufacturer? Read the problem carefully. I can get at least 400. Because that set of words, if you said I can get 400, should I be doing a left, a right, or a 2? That'd be a 2. They said at least, which makes it, because I'm claiming we might get less. Now, I need, yes, sir.
I was reading the question. I'm not seeing where it says at least. It just says that it claims point code coverage of 4 square feet per gallon.
Right, but when I actually read the can of paint, it does say at least. You want to do a 2-tail? But I'm thinking about the way you buy the. You're right. The words are not in there.
Yeah.
So that's a good question. Did I misread? I'm confusing 2 problems apparently. Yeah, if you look at 38, 38 says at least verbatim. That's why I got caught. My apologies. I screwed up. So, should we do a left or should we do a 2? Would you be unhappy if you had extra paint at the end of painting something? So that's okay. If I get more than 400, I'm happy about it. It's only when I get less than 400, I'm unhappy about it. I think I'm going to stick with a 1-tail and I'm going to use a left because the low end is what's going to bother me. Good catch. If you'd done a 2-tail and I'd gone, you could argue that with me, absolutely. 2-tails are harder to reject the null hypothesis than 1-tail are. So if you do a 2 and you reject, well, then you know you would have rejected on the 1 as well, right? Okay. I need 2 pieces of information. Just like the z-test, I now need to do it in t, 2 pieces of information. I need my calculated t-value. Let's do that. I need my average and standard deviation. I don't have those, do I? Let's make those. Might as well do it the easy way. Here we go. We'll put in our 6 pieces of data, 360, 410, 380, 360, 390, 400. And then we can ask for the average of these pieces of data. There's my average, 383.3. And I can ask for the standard deviation. Now, if I'm going to do a standard deviation, which of those two standard deviations am I going to do? Dot P or dot S? Exactly. I'm going to do the sample one. DEV dot S parenthesis. Same numbers, 20.66. And now I can do the T calculation. By the way, I don't have to do it by hand. I don't have to do it with my calculator. I can do it right here. Equals my average minus the benchmark. What was the benchmark? 400. Divided by the standard deviation, divided by the square root of how many? Now I can count them, right? But I also have Excel count them. Square root of count my set of data. One, two, third set of parentheses. That's my T value. How do I get the critical value? I can do it in Excel, I can do it on the table. To do the critical one, I need to ask it, hey, if I wanted a 10% area with the degree of freedoms being 5, because degree of freedom is 1 less than the number of things, I could say I want the inverse. T dot, there it is, INV. Notice there are two versions. There's a T inverse and a T inverse 210. So if I tell it I want to do the inverse, I want an area of 0.1. That's my significance. And then my degrees of freedom goes next. In absolute value, which is bigger, my calculated or my critical? Right. And if we think about this being on the left, what that means is I'm further to the left than my cutoff. My cutoff, am I in the left reject region? Yes, I'm lower down. In absolute value, take a picture, flip it over here, make those numbers positive. Oh, yeah, I'm too far out. This number is closer to 0 than this one. We are outside. So what do I do? Do I accept the manufacturer's claim or do I reject it? Am I in the shaded region or the unshaded region? I'm in, yeah. So now I go back to the picture. I'm down here in this little tiny shaded region. Boop. Down here. Well, I can think of it as being more negative, but then I have to remember that which tail I'm on. And if I throw the absolute value in, it's always that side. I just tend to think of it, oh, as being up here. But that's because I like positive numbers. If you are okay with negative numbers, you can say, oh, this is more negative. We're further away. I rejected it. And if I reject it, what does that mean in our situation? in this problem setting, talking about paint coverage on walls, right? If we rejected the null hypothesis, Tony?
That it makes less than what per gallon.
The 1 gallon doesn't give me 400 square feet. It gives me less than that. Chris, what if I'd done a two-tail? What if I'd done a two-tail? Let me go back here for a second. The T-calc isn't going to change. The only thing that changes if I do a two-tail T dot INV dot 2T. Same numbers, 0.10, comma 5. First of all, this always spits out a positive number. But if I'm doing a two-tail, then there's a positive version and a negative version. Right? Because there'll be one on each side. What does that one tell us?
Our calc is less than our grid, so we would accept the hypothesis.
I can't reject. So my choice of test matters. Because then we'd say, oh, that 10% chance is really a 5 low and a 5 high. And I didn't get a 5 low. I'm at 1.976, and we want to be down at negative 2.015. I didn't get far enough down. I'm still in the white unshaded good region. I can't reject my null hypothesis. So my choice of test matters because two tails make it harder to reject the null hypothesis. And this is exactly on that border case.
So the detail basically shows us the region we don't want to be.
The two-tail means that the 10% is broken up to 5 and 5, right? Instead of one big area, we have two smaller areas. So our cutoff here was 1.476, but our cutoff here was 2.01 because I needed to cut out more of this area, right? To get it down instead of being 10% in one blob. That in the one tail, our T calculate was in here. In the two tail, it was here. And so that meant we couldn't reject. It where the line got drawn changed because of which kind of test we were doing. On our table, by the way, take a look at those significance values at the top of the table on Appendix D. It says rather bluntly, a one-tail test versus a two-tail test. Notice that the numbers in the one-tail test are half the size of the numbers in the two-tail test. Because if I do a 10% one-tail test, that's putting 10% in one blob. But if I had two of those blobs, that would be 10% at the bottom and 10% at the top. It would be a 20% for a two-tail test. So the size of our region changes depending on whether we do one or two. Now, notice degrees of freedom 5, 10%, 1.476. That's the same critical value, isn't it? So I could have done this right on here instead of in Excel. By the way, I do it here too. We did all of these tests on paper using our tables because we had to look up all the information for our critical values. But that's just the calculus shading in the curves, right? If I go to the stat button again, where we did our lists to do the descriptive statistics, there's a column heading over there all the way on the right. It says test. And lo and behold, those first two options are exactly the tests we were doing Friday, just now. I'm going to do the same t-test we just did. Now, I could give it the actual data. If I said I was going to give it the data, it would ask me, where did you put the data? I haven't put the data in yet. So let's quit out of this for a second. Second, quit. I'm going to go back to stat, and I'm going to go to that first list, edit. And in the first list, I'm going to put our numbers. Our numbers were 360, 410, 380, 360 again, 390, and 400. Just like I entered them into Excel, right? Now I go back to stat and I do the t-test. My information is in list 1. My benchmark is 400. Am I doing a 2, a left, or a right? Oh, I was doing a left. It will actually draw the picture of the t-distribution and do the shading. If you hit the draw option, I'm going to do the calculate option. T, 1.976. Isn't that the same one we got? There's X bar and the standard deviation and the number of things. They didn't tell me accept or reject. Why not? Because they didn't give me the t-calc. What they gave me instead was the p-value. The same p-value from the t-curve that we would have gotten from the normal distribution. They did, what is the chance of getting this? And it's 0.0525. What was our significance? Is that smaller or bigger? So we reject. And see why now a two-tail test would have given me a different answer? Because if I'd done a two-tail test, my p-value for rejection would have been twice that number. And 2 times 0.0525 is 10.5%. And that's bigger than 0.10, so I don't reject. Yay! By the way, if instead of doing this version, we give it the statistics, then we have to give it the average and the standard deviation. Now, since we just calculated those, it's kept them in memory, but if we type them in, it would do the same calculation. If I had already worked out the average and the standard deviation, like in the light bulb problem where we were told the average lifespan was 3,000 was our benchmark, and this batch had a average of 3,515, I could put those numbers in. That was a z-test, though, not a t-test, right? So I would actually put it in this version. Same setup, but notice instead of sigma, instead of S. So I can actually tell it, oh, the population standard deviation is already known. I like my technology. But this works really damn well. I'm very happy to have this piece of paper too. All right, time to write down some summary information. T-calc, negative 1.976. T-crit, negative 1.476. T calc in absolute value is bigger than T crit. Reject. Now, here's a question. This is statistically significant. Is it practically significant? How many walls are you going to paint? If you're going to paint a lot of walls, you're going to buy a lot of paint anyway. And if you're off a couple of square feet in each direction, well, maybe you end up being short a can of paint by the time you're done painting a lot of walls. If I had to paint this entire room, I'm pretty sure there's more than 400 square feet of wall in this room. I need to know whether or not I could trust this coverage. On the other hand, if I'm painting my office, which is a tiny little closet, I don't have to worry about that. It's got very small walls. So while I have a statistically significant result, do I have a practically significant result? We said the average was 400 square feet, and I'm getting 383 square feet, 17 square feet. It's not a trivial amount, but in the long run, I don't know. So quite frequently, that's the question we end up asking. Not just, what's our result, but now what do I do? That's the value judgment part that the statistics can't answer. As a mathematician, I'm happy to go, here are the numbers. But as a business person, as an employee of a company, my comment is then, now that I know this, what do I do? And that's a value judgment. That's going to depend on you and the morals you have and the morals of your company. And that's where you get to decide how good of a person you're being. No, people should smoke more. It's going to keep us in business, man. Even if I'm not talking about smoking, let's talk about additives to gasoline. Do you know the most common prevention for engine knock? I don't know. Do you know what engine knock is? If you turn off your car and the pistons keep firing, your engine a couple of times after you've turned the key off, that's engine knock. Excess gasoline is still firing in your engine. The easiest way to prevent that is to add lead to your gasoline. Literally, lead in solution. That's why the gasoline you buy is called unleaded, because they took it out. Why? Because it was poisoning people. And that's dumb. Really nice, bright white paint is made white like that from lead. Lead paint chips. Same issue. Do you know the best green that was ever made was made using a dye that contains cyanide? It's a beautiful color. Green wallpaper was everywhere. It was beautiful. Kept killing people. It's a bad idea. Care about white paint coating on the walls. I care about this sort of connection. Make a business decision. Two other things, but they'll go for next time. I've done means two different ways. I've done averages where I know the population, standard deviation. I've done them where I don't. I now have, what if I'm doing a proportion? And then what happens if I lose my ability to decide whether or not my population is normal? But those will be what we discuss on Wednesday. I will see you all then. A wonderful rest of your day.